Okay, so I guess, all right, great. Pardon me. All right, everybody. So forgive me, I'm using Dr. Bindi's slides. They're not exactly the way I would have worded things or necessarily exactly the way I would have said things, but I wanted, for consistency, I wanted to follow her slides and what she's doing. So let's see here. All right. So we are going to introduce a new quantity, a new physical quantity today called momentum. And first of all, we already learned from conservation of energy that we can solve a lot of problems with it, right? Many, many different types of problems. We can answer a lot of questions with that. But it turns out that when objects collide with each other, or when objects explode apart from each other, energy is lost in that process, okay? Partly because as objects collide, oftentimes they do not spring back to their original shape. They absorb energy as they deform or as they get a little hotter as a result of the collision. So all of that stuff takes away energy from the system, and the amount of energy it takes away is complicated. Right? There's not like a nice little simple formula we can use for that. Okay. Sometimes objects stick together, so the mass of the objects in the system kind of changes, right? So it turns out that there's a limit to what we can solve by just saying, okay, energy is conserved. However, fortunately, there is another physical quantity which is conserved in collisions, explosions, or any other brief interactions where objects exert forces on each other. And it turns out that quantity is linear momentum. Okay, so we're going to define momentum as lowercase p right here. Lowercase p is equal to the mass of an object times the velocity of that object. Now we all know that mass is a positive scalar. So what that means is, since velocity is a vector, momentum is also a vector, and it points in the same direction as the velocity. Okay, so that's what this says down here at the bottom. Okay. Also, if we look at what the units should be for momentum, it should be the units of mass times the units of velocity or speed. So it's kilograms times meters per second if we want MKS units. We don't have a special name for this particular momentum unit, so we just write it out as kilograms meters per second. All right, so what do we get from this? We get that if you have two cars of the same mass and one is going twice as fast as the other, then that faster car has twice as much momentum. On the other hand, if you have two cars going the same speed on the freeway, one is a small little compact car and the other is a really big SUV with twice the mass, then the bigger car can have twice the momentum that way as well by simply having more mass. So it's this interesting combination of mass and speed. All right. Here's a couple examples of just calculating change in momentum. And this is something you might be asked to do for a particular problem, right? Whenever you see delta P, that delta means, just like it did in all of our other previous instances, it means P final minus P initial, okay? When we talk about the change in momentum of an object, as it's struck, like let's say a tennis ball as it's struck by a racket, or a golf ball as it's struck by a club or something like that, we're talking about just before impact to just after the impact is done. And so if the objects are going to separate right after they separated, okay? Or if the objects aren't going to separate, like the teddy bear and the floor, when the interactive impulsive force between them has died away down to some minimal zero or equilibrium value. All right, so right before, if we consider all these velocities to be y components of velocity, then we can see that, and then these become y components of momentum. Our textbook often likes to write all the little y subscripts, but I will often just leave them off when it's understood. And I'll give values positive if they're in the positive y direction, or negative if they're in the negative y direction, okay? So it's understood that these are components. And this is a one-dimensional problem. All the movement here is along the y direction. So we can say, okay, what's the teddy bear's momentum right after it hits the floor minus right before it hits the floor. So right after it hits the floor, its momentum is equal to m times v final, which is 0. Right before it hits the floor, it's equal to m times v initial. So whatever that negative value is, right? V initial is downward. So 0 minus negative mv is equal to just m times v. Notice that for the bouncy ball right here, the final velocity and final momentum is m times positive v, whereas the initial velocity, initial momentum had a negative v. So as a result, when we calculate the change in momentum of the bouncy ball, we get 2 mv instead of the teddy bear, which is just mv. And this is assuming that the ball and the teddy bear have the same mass here, okay? So that's really interesting. When something rebounds off of a surface, we can see that the surface not only has to absorb all of the incoming momentum, but then the surface and the ball together have to then provide the return momentum as well, okay? As opposed to if we have an impact where things stick, then the surface only has to absorb the incoming momentum. So there's a really interesting difference in change in momentum in these two cases. In fact, we could put a little scale here, or we can make some measurements, and we could find out that the amount of force and or the amount of time that the floor has to push back on the teddy bear is going to be about half as much as the force and or time that the floor has to provide for the bouncy ball, okay? So the bouncy ball will be twice as much as a teddy bear. So in other words, the change in momentum that these two are undergoing is different. So what causes that change in momentum? Well, that leads us to the next slide, okay, which is the answer to that, which is in order to change the momentum of an object, a force must act on it, okay? And specifically, we can get units of momentum if we take force and multiply by time. So if we take newtons times seconds, we end up with kilograms meters per second. We call that quantity often impulse, right? Although really that's just a fancy term for some amount of delta P, change in momentum, that the object receives as a result of the impulsive force acting, okay? So sometimes people will call that force that's doing this change in momentum, the impulsive force. So if initially we have some leftward momentum to this baseball at some initial time, and then after it's struck by the bat, it has some rightward momentum, what that means is in between, there had to be a time in the middle here where the ball and the bat, so here's the end of the bat, and here's the ball, that bat had to exert some sort of an impulsive force on the ball at that time, okay, over some very, very brief period of time, usually. Okay, so we take the average value of that force, multiply by the time that the bat and the ball are in contact, and that product gives us the change in momentum that the baseball undergoes. All right, so just to sort of write this out as a formula on the next page right here, okay, the definition of impulse, which by the way, Dr. Bindi's slides have capital I, but our textbook uses a capital J. Oops, sorry about that. Use a capital J. And other textbooks and in my own solutions, I just use a delta P because I don't want to introduce another variable for something when we already have a variable for it. But unfortunately, capital J is in very common use. So just be prepared to see it when you look at at our textbook or other materials, okay? We can just say, all right, the amount of impulse that an object receives is just equal to the impulsive force times the time that impulsive force acts, okay? Now, in reality, the force starts out when the baseball bat first touches the ball, that force is really weak. Then as the ball sort of mushes up against the bat, that force gets stronger and stronger. And then as the ball finally springs off from the baseball bat, then that force again drops down to something very weak and then 0. For physics 151, we're not going to worry about the fact that that force has some varying value, strength over time. We're just going to take the average. Okay, we'll just worry about the average amount of that force. Okay. All right. And once again, if you take force times time, we just get the units of momentum again. We can see that, again, we know that momentum is a vector. Therefore, the change in momentum that the object receives is always going to be in the same direction as the applied impulsive force. Okay, so if the baseball bat is hitting the ball to the right, if the bat is exerting a force on the ball to the right, then the ball is going to have a rightward change of momentum. So that's what this is saying right here. All right, so once again, impulse, kind of just a fancy term for change in momentum of an object as a result of a force acting for a short period of time. Okay, now it could be a long period of time, but we're always going to sort of in this class assume very short periods of time for reasons that'll become clear coming up when we talk about conservation of momentum. Now, to sort of foreshadow what's coming on the next slide, if we were to take this expression here, if we were to take this expression and just move the delta t over to the right-hand side, what would we get? We would get that that if an average force acts on an object, then, and if that's the only force acting on the object, that force would cause a rate of change of the object's momentum that's equal to delta p over delta t. Suppose we had multiple forces. So suppose we had force number 1 doing this, and suppose we had another force, right? That could, if it were acting independently and separately, cause a different change in momentum of the object. And we could imagine multiple forces all acting on an object or a system at the same time, which in and of themselves could each cause a different change in momentum of the object or the system. If we were to add all those up, what would we get? And that takes me to the next slide, which is if we add up the net force acting on an object or a system of objects, then once we balance out all the forces and get their sum or their net or their total, that gives me the total or net change of momentum of that object or system. Okay. Now, this left-hand side here, the sum of external forces or outside forces acting on an object or on a system should sort of ring a bell with you, right? I hope that it reminds you of the start of Newton's second law. So all we did before is we said, okay, the sum of external forces or outside forces acting on mass m, however we define mass m as a single mass or a system of masses, results in acceleration, right? So this is just another way of recasting the right-hand side of this equation. Now, for the simple cases that we're mostly going to be dealing with here in Physics 151, the mass of the object does not change, okay? So the mass of the object will stay constant. And if we do that, then what this numerator becomes is a constant mass times change in velocity over time. Oh, and behold, this is just acceleration, right? So it turns out if we keep the mass of the object or the system constant, then these two formulations of Newton's second law are the same. Okay, they're exactly the same. It's just another way to write Newton's second law. There are more advanced situations that they're covered in like Phys 170 in the calculus-based class where you could consider a system where the mass itself has some rate of change, like a rocket that's burning fuel, right? So the mass of the rocket decreases over time. And in that case, we can't just make such a little simple equivalence, right? And in that case, this is the form of Newton's second law that's used for rocket problems. All right, but for Physics 151, we're going to just assume constant mass for all of our objects. So it turns out that either of those formulations of Newton's second law are equivalent in our case. All right, now let's consider what this means if the net force on the left side were equal to 0. If this left-hand side were equal to 0, then, so in other words, you either have no forces acting on an object or you have multiple forces, but they all add up to 0, right? When you add the vectors. So they balance each other out, in other words. Then what would it mean to say that the momentum of that object or system is unchanging, right? Well, what would it mean to say delta P over delta T is 0? It means that the momentum of that object or of that system of objects is fixed over time. It's constant. So what that would mean is that delta P is 0. So that means that P itself is constant. Okay, so the momentum of that object or system of objects, if you have a system, which is what we're usually going to have with collisions, is constant. So that's going to lead us to what we call the conservation of linear momentum, to be more precise, or just conservation of momentum. When we just say conservation of momentum, it's assumed we're talking about the value p, which is our linear momentum. All right. So if the net, let me just say it one more time, if the net external forces or outside forces are zero, or are so close to zero that we can basically just make that approximation, then we can say that the total momentum of the system is fixed over time. All right. So we're going to show how that gets put to use with a couple of examples. Although I think I have one more slide here that just has the statement of that one more time. Okay. So if we have, instead of just a single object, if we have a system of objects and we talk about the external forces, right, that on the previous slide, this is the external forces acting on the outside of the whole system of objects, okay, then what we can say is, all right, if that sum of external forces is zero, then the sum of all of the momenta of all of the objects at any final time, so you can see this left-hand side is the sum of the momenta at any final time, at any later time, is equal to the sum of all the momenta of all the objects at any earlier time. Notice that that's what the little I is for initial. Okay, so that is conservation of momentum when we can make that assumption that the sum of all the external forces is zero or essentially zero. There's an extra point here, which is that internal forces can definitely not be zero. So in other words, if we have a system of two or more objects, they can all exert internal pushes or pulls on each other. And any changes in momenta that those cause of those objects, of those individual components of the objects, will always sum out to zero, right? So one of the internal components might get some additional momentum pushed to the right, but at the same time, one of the other internal components will get a push to the left. And when we sum all these p vectors together, any changes as a result of internal forces balance out, okay? All right, so we can still make this statement of conservation of momentum. All right, so what that means is if we have two objects collide, any internal collisional forces between those objects does not change the total momentum of the system. And we can still say that the sum of all the momenta is unchanged. All right. Okay, let's take a look at a couple of brief examples before we start officially calling them collisions. All right, so suppose that we have, actually, this is like a very small explosion. Okay, suppose that we start off by having an astronaut holding a metal panel or solar panel, pardon me. The astronaut has a mass of 60 kilograms and the panel has a mass of 80 kilograms. Okay, all right. Initially, they're both at rest. So they all start off at rest, as you can see right there. Okay. Then the astronaut gives the solar panel a shove. And assuming that the panel goes to here, if we just follow this picture that's drawn right here, the panel will go to the left at 0.3 meters per second. And then the question is, what is the astronaut's final velocity, okay, going to be? Now, first of all, we can see from this little cartoon, or we know also from everyday life, that this is a recoil problem, right? If we imagine, notice that the panel is the heavier object and the astronaut is the lighter object. So what I want you to do is imagine that the panel is kind of like the gun, if you will, holding the smaller bullet, and the astronaut is like the smaller bullet, and they both start at rest, right? Or you can imagine any other thing where you have a larger housing that's going to launch a smaller projectile. Then the launch happens, or the explosion happens, right? The smaller projectile is going to move to the right. And what happens to the housing, or in this case, what happens to the gun? It's going to recoil and have a kick back to the left. Okay, so that's what's happening here. This is a recoil problem, if you will. All right, so we're given all of the masses, we're given the initial velocities of both, and we're given the final velocity of the panel. So we're given everything except one unknown. So let's solve for that one unknown. And the way we do that is use a statement of conservation of energy, of momentum, pardon me, conservation of momentum. So using the formula from the last slide, we're going to add up the momenta of all of the objects after the explosion happens, and set that equal to the sum of the momenta of all the objects before the explosion happens, right? Before the launch. Now, I'm going to go, technically, these are all vectors, but in Physics 151, we're always going to just do one-dimensional problems. So what we're going to do is say, all right, although I'm not going to write little X subscripts on everything, I want you to remember that all of the velocities and all the momenta that we're writing are all just X components, okay? So these are just X components. And I'm going to drop all the X subscripts off because otherwise it's just too many subscripts, okay? All right. So what we want is the final momenta of the panel and of the astronaut. So we have mass of the panel, velocity of the panel final, and then mass of the astronaut, velocity of the astronaut final. Now remember, these velocities are X components. So that means they can be positive if they're to the right or negative if they're to the left, right? Before the explosion happens, right? If we were to write it all out, and I'll do this once, right? We'd have mass of the panel times the velocity of the panel before the launch, and then mass of the astronaut times the velocity of the astronaut before the launch, okay? But whenever objects are stuck together, it's unnecessary to write their velocities as separate, distinct velocities. We can usually merge those into a single velocity whenever objects are stuck. And you'll see that coming up in the next example. Okay. Now, in this case, we're told that they both start at rest. So we know that these are both zero velocities right there. And now we can solve for what we want, which is the final velocity of the astronaut. So that's the unknown that we're trying to solve for. So let's do that. There we go. That's the answer. Right. Now, again, bearing in mind that these are X components for the velocities. Okay. Right. So now all we need to do is just plug in the values. Mass of the panel is 80 kilograms. I can't tell how many sig figs are on these things. We'll just assume 2 sig figs. Velocity, final velocity of the panel is to the left, right? Again, these are X components. So just using the picture here as my guide, I need to make sure that that final velocity of the panel is negative 0.3, okay? Because it's in the negative X direction on my picture here, right? And then the mass of the astronaut is 60 kilograms. And when I solve for this, I'm going to get that the final astronaut velocity is going to be positive 0.4 meters per second. Okay. Aha. Good. That matches what we expect, that the astronaut recoils to the right, right? Well, I guess you could say the astronaut is launched to the right if you think of the astronaut as a smaller object, and the panel recoils to the left, right? However you want to sort of think about which the objects is the projectile, which is the housing. All right, good. So notice by keeping careful track of my signs, I was able to get a usable sign on my final velocity. Sometimes in these momentum problems, we don't really know what direction that final velocity is going to be until after we solve the problem, and then we see what the sign is. All right, let's do another one. Okay, now this one is similar in that initially everything starts at rest. We have a honeybee with a mass of 0.15 grams, and we have a popsicle stick with a mass of 4.75 grams, okay? And everything starts at rest. Right. Then what happens is a little internal force arises, if you will, between the honeybee and the popsicle stick. When the friction from the honeybee's legs, right, go into action. And what that does is it pushes the honeybee to the right, and it pushes the popsicle stick to the left at the same time. If any of you have ever stood in a rowboat or a canoe, when you start at rest, and then if you start to walk in one direction, what happens? The boat or the rowboat or the canoe will go in the other direction at the same time, right? Or you can do this on a skateboard too, and the same thing will happen. Although in that case, the skateboard has a lot less mass than you do, so the skateboard really launches fast and you barely move. Okay. All right. You should be very careful when doing this. This is a dangerous experiment. All right. So the final situation that we have is the honeybee going to the right at some velocity and the stick going to the left at some velocity. And we're going to use their definition here of the positive x direction to the right. Right. And then the question is, what is, given all of these values, what is the final velocity of the B to the right? All right, so I'm going to follow a very similar path to the last problem. Conservation of momentum. I'm going to say the sum of all the momenta of all the objects after that internal force is applied, okay, is equal to the sum of all the momenta of all the objects before that internal force is applied, okay? We're assuming that there is no external forces from water drag or air drag or anything like that, at least during the brief period of time that the little internal force of the bee's legs is being applied. You know, it could be once the popsicle stick is kind of cruising along, the water drag quickly acts on it and brings it to a halt. But during the application of the impulsive force of the bee's legs, we're going to assume that during that brief period of time, we can neglect all of those frictional forces, that all those outside external forces are approximately zero, and that we can therefore say that the momentum of the system is roughly constant. All right. After that, so after the sort of internal forces are applied, we can say we have mass of the bee times velocity of the bee final plus mass of the stick times velocity of the stick final. And again, these are all x components. So I'm dropping the x subscripts off of everything, but I want you to remember in the back of your mind that these velocities here could be positive or negative. And then before the collision, before the impulsive force is applied, we have mass of the bee plus mass of the stick, and they all start off with the same initial velocity of 0. So I'm just going to, here I am going to combine them, okay? And just say, look, one object, both objects have one common velocity at the start. Okay? So they start from rest. All right, so now let's solve for what we want, which is what's the final velocity of the bee? Great. Physics is done. Now it's just plugging in the math numbers. Now, I want to mention one thing here. The masses and the velocities here are given in CGS units instead of MKS units, right? The beautiful thing about this conservation momentum equation is there's no constants in it, right? So I'm not plugging in any constants in MKS units like little g or big G or anything. As long as all of my masses have the same units, it could be any unit I want. I could use, slugs, or I can use kilograms, or I can use grams or micrograms. I just have to be consistent. Same with the velocities. As long as all the velocities have the same units, then I can use any velocity units I want, centimeters per second or miles per hour or whatever I want. Okay, I just have to be consistent. That way the units will cancel properly. But I'm not compelled to convert everything to MKS in this case. So mass of the stick, 4.75. I'll just leave it in grams. Velocity of the stick at the end is to the left, according to the little picture up above. Notice how important it is in this case to have a sketch and to have the positive x direction defined in that sketch. And then the denominator here is mass of the bee. Notice how the grams are going to cancel. Let me show you. And notice how I'll be left with centimeters per second for my final velocity, which is fine, right? That's actually kind of useful. The two minus signs also cancel each other out. And my final answer should be positive 3.8 centimeters per second. Sanity check, is the bee moving in the positive x direction? Yes, good. Sorry, my handwriting looks so terrible here. I'm sorry, it's just using the tablet and the stylus is, in real life, it looks better. It looks like the solution sets in real life. It looks like the solution sets for the tutorial sample problems. Okay, so what we've had with the astronaut and the solar panel, or with maybe the bee and the stick are sort of explosions, right? Where there's an internal force that's applied and the objects kind of, move apart from each other. Collisions are times when objects have velocities to start with, and then they interact with each other, apply force with each other, as a strike, right? So it turns out that as they strike, some, well, most, if not all, real life, macroscopic real life objects end up losing some amount of kinetic energy in that collision. And like I mentioned at the very start, during the first slide, some of that energy is lost to the internal heating of the objects, right? The little molecules and atoms are not jiggling faster after the collision than they were before. It can also be lost to permanent deformation of the objects. It can also be lost to sound waves that are carried away from the collision, let's say through the air or through the surrounding medium, okay? So all of those things steal away a little bit to a lot of the kinetic energy of the two objects before they collided. But as long as we can make the assumption that the external forces outside the objects are small enough and weak enough compared to the massive internal force, the impulsive force of the two objects colliding, and that the time that impulsive force acts is brief enough, then we can basically disregard those external forces. And we can make the nice assumption that the total momentum is conserved. So even if the objects stick together, like a bullet embedding itself in a tree or two cars sort of locking together in a collision, the nickname for that is a completely inelastic collision. Okay, even in those cases, net momentum, total momentum is conserved, even though a large amount of the kinetic energy is lost. If the objects do bounce apart from each other, but they are real life objects, they will still tend to absorb and dissipate some amount of the kinetic energy. Okay, but it's not as, they don't soak up as much of the kinetic energy as when the objects stick. We call that just generically an inelastic collision, right? Or here it's called partially inelastic. Okay, when you hear the term completely inelastic, they're referring specifically to things sticking, right? Then we can imagine a case where the objects behave, when the objects collide, the place where they collide behaves kind of like a perfect ideal spring. It might smush and compress, but then as the objects spring apart, 100% of that initial stored energy is returned entirely to the motion of the objects. In that case, kinetic energy of the objects after the collision will be exactly what it was before the collision. Not individually, but the sum. The sum of the kinetic energy of the objects after they collide is exactly what it was before they collide. They could pass kinetic energy to each other in the collision, but none will be permanently lost to any of that deformation or other dissipative things that I mentioned before. Okay. All right. That's called a perfectly elastic collision, or an ideally elastic collision between the objects. This actually does happen in real life between atoms. Okay. Or if I have two magnets that get close to each other and repel each other, right? Or two electric charges that get close to each other and repel each other, but they don't actually like strike, right? They get really close and then they get pushed apart. That electric field or that magnetic field behaves like a perfect ideal spring. It temporarily stores up the energy and then it gives all that energy 100% back to the objects. In real life, we can try and mimic that with things like springs, like real life springs. But as you know, real life springs are not quite perfectly ideal. Or when pool balls or billiard balls strike, or steel balls strike each other, they're close. They're close to elastic, but this is never exact, right? So we always lose a little bit of energy in that sort of case. So you're going to see a cartoon on the next slide where it shows pool ball strike, or a few slides from now where it shows pool ball striking, but you have to keep in the back of your mind that that's an idealized case. Okay, and in real life, even pool balls don't have even billiard balls don't have perfectly elastic collisions. But individual atoms do. Individually, they do, or individual molecules do, or individual particles, like two electrons striking. All right. Okay, so summary, elastic, all right, all collisions conserve momentum. Only elastic collisions also conserve kinetic energy, whereas all inelastic collisions, which includes really all real life collisions, will dissipate or lose some amount of that kinetic energy. All right, let's see that put into practice. So here is a completely inelastic collision. Suppose we have two train cars, and in this case, they have initial velocities, and they have some initial masses, mass 1 and mass 2, and then they strike. And when they strike, they lock together. So now they move as you could think of it as a single object if you want, right? So although conservation of momentum, if we were to write it all out, would look like this. If we choose a positive x direction to the right, m1 v1 initial plus m2 v2 initial is equal to m1 v1 final plus m2 v2 final. This harkens back to what I mentioned before. When you have two objects moving as a unit, then what we can do is just combine their masses and, oops, looks like I did something to my tablet. Okay. Looks like we can just combine their masses and then write their velocity as a single velocity afterward. Okay. So notice how they dropped the 1 and the 2 off of that velocity because it's just assumed that that is just a single velocity. All right, let me see if I can fix my tablet. Just a moment. Okay. All right, I think it's back online. All right. This is just solving for v final in that same equation. Okay, so there's nothing really new on this slide. Let's skip it. If the objects don't stick together, so ignore this picture and ignore this derivation. Okay. If the objects don't stick together, then we have to leave their two velocities separate at the end. So the conservation of momentum equation becomes this equation up here at the top, right? And what I would do is, if this were a question for this class, we would give you all of the individual pieces of information except for maybe one unknown. So you would just have to solve for that one unknown, okay? But you would have everything else. You can do a little bit of algebra, and what you can show at the end of all that is that the kinetic energy of the sum of the two objects after the collision is done will always be less than the kinetic energy of the two objects before they collide. So that's what we said on the previous slide. But you can just, if you want, you can show it mathematically that it has to be true. Okay. So I'd like you to not worry about this derivation here. Okay. Just know that this is a fact. All right, let's do an example of conservation of momentum when the objects stick together. Okay, so here we have two football players, and they have, again, we're choosing the positive x direction to be to the right. Okay, they have masses m1. So this is m1, and then this is mass m2. So that's mass m2. And notice that their velocities, right? Velocity v1 initial before they collide is positive. It's in the positive x direction, and v2 initial before they collide is negative because it's in the negative x direction. Okay. Now the question asks, what is their velocity if they collide and they lock together? Okay, so this is what we call a completely inelastic collision. Then what is the velocity of the joined together masses after the collisions, right? After the collision is done. So after that internal force acting between them has arisen and then died down, which only takes a few, tenths of a second, maybe. Okay. Then what will be the velocity of the two joined together masses? And then after that, we can check out their kinetic energies, which is the second part of the question. So let's start with conservation of momentum, which we know is true for every collision. So the sum of all the momenta after the collision is done must be equal to the sum of all the momenta before the collision occurs. Right? So after the collision is done, they move as a single object. So I'm going to use that trick from the previous slide where I just say V final, period. I don't need to specify V1 final or V2 final because they move as a single object. And then before they collide, they had different velocities. So I have to say V1 initial separately from V2 initial. Okay. All right. Well, actually, to be honest, the physics is now done. We know all of these values here except for V final. So now we can just solve, right? In this case, what I might do is instead of doing the algebra first, I might just plug in the numbers first and then find out what it is. So this is going to be 95 plus 111 kilograms times V final. That's our unknown right there, is equal to 95 times positive 3.75 meters per second, right? That runner was moving to the right, and 111 times negative 4.1 meters per second because that runner, the other runner was moving to the left. Okay. I use my calculator, grind through all of that, and what do I get? I get that V final of the two masses that are stuck together is equal to negative 0.48 meters per second. All right, so that's very interesting. Not only have I found how fast the two of them are moving, which is pretty slow compared to their initial speeds, right? Their initial speeds were both around 4 meters per second, but afterward, they're only going a half a meter per second when they're stuck together. And we find out that it's to the left. So it turns out that this onrushing player number 2 is actually able to get player number 1 to reverse direction, albeit slowly, right? So player number 1 was moving to the right and then gets stopped and slightly pushed backward, right, to the left. If we were to actually calculate what all of the kinetic energies are, at this point, that's just kind of just a lot of math, okay? But what we can find is, all right, the sum of all of the initial kinetic energies is going to be 1/2 m1v1 initial squared for the player on the left who's oncoming, and then 1/2 m2v2 initial squared for the player on the right who was oncoming. We can plug in all of the values, all that was given in the problem. And when we grind through all that, we find that they had 1,600 joules of kinetic energy before they collided. And then we can find out what the sum of all their kinetic energies is after the collision is all done. And the nice thing about this is I can now treat this like a single object. So at least there's a little less math to do. And then plug in all those values, and I find that it is shockingly less. The amount of kinetic energy left in the two of them after they're stuck together at the end is only a tiny fraction. It looks like it's about 1.5%. It's between 1 and 2% of the original amount of kinetic energy. So 98 to 99% of the initial kinetic energy was lost. So the change in kinetic energy in this case is equal to negative 1576 joules, right? I would actually probably round that off a little bit because we lose some sig figs. Okay. All right. So this just goes to show that you can do this for any collision where the objects stick together, and you'll always find that there is a loss of kinetic energy in that collision. All right. Well, I think that's the last of the numerical examples that I'm going to show. I'll just say a few more words about elastic collisions, and then that'll be our stopping point for today. So remember how inelastic collisions are ones where some amount of kinetic energy is lost, right? And that real life collisions are always that way. However, you can imagine perfectly elastic collisions, which actually, like I said, do happen between individual atoms or individual particles, where momentum is conserved and the total kinetic energy is conserved. So what we get then is two equations. We get conservation of momentum, right? Oh, and by the way, in elastic collisions, the objects will always separate afterward, okay? So it's impossible to have, if the objects stick together, it will be inelastic for sure, okay? Whereas if the objects separate, it could be inelastic, or in ideal cases, it could be elastic. So the objects do separate in the elastic collision. So we have conservation of momentum. And then if we calculate the sum of the kinetic energies after, we'll find that the sum of it's equal to the sum of the kinetic energies before, because any temporarily stored energy in that collision gets returned to the objects. All right, so we have two equations. Now notice the unknown, the variables in these two equations are all the same, right? The masses and the velocities are the same in the two equations. What distinguishes the equations is the fact that in the kinetic energy one, they're all square, all the velocities are squared, right? And there's a bunch of 1/2s in there, but as you can see, all the 1/2s will cancel. So you could solve these, right, in various ways if you know all of, if you're given all of the values except for one unknown. Or you could actually be given all the values except for two unknowns, and then you have two independent equations with two unknowns, and then you can solve them simultaneously. And the algebra gets a little tough. Dr. Bindi points out an interesting little kind of algebraic result that you can get if you combine, here's the second equation, kinetic energy, rearranged a little bit. And then if you unfoil these algebraic, these sort of polynomial parts here, right? You can see, this is equal to that based on the first momentum conservation equation. And when you set all that, when you simplify this after canceling that, you can find that the relative speed of the two objects before they collide equals the relative speed of the two objects after the collision is done, which is kind of a beautiful result that you get only in the case of the elastic collision. Okay, even if objects have different masses, that relative speed difference thing still applies. So that's kind of a nifty result. If you do an example of elastic collision where you calculate, you're given the initial speeds of these two objects before they collide, and you go through all the work and calculate what their speeds are after they collide, you can see that the separational speed between the two was 3 meters per second before, and it's 3 meters per second after. So it's kind of a neat result. Okay, you don't need to memorize that for our class. Okay, and most, unless I specifically say that it's an elastic collision, you can assume all of the collisions that we're going to be dealing with conserve only momentum, right? That they're all inelastic. All right, so that's where we're going to stop. That basically covers the topics that we wanted to have for lectures 22 and 23. And lecture 24 is center of mass. And I think that Dr. Bindi is going to pick up with that on Monday after spring break. Great, thanks for coming.